Have you ever wondered what makes an airplane fly? Well, the answer is lift. But what is actually lift and how is it generated? A common way to describe lift is using Bernoulli's principle. So let's say you have a wing and the air is hitting the wing and moves above and below the wing. So the general idea is that the air above the wing moves faster, and because the air moves faster, a lift is generated, and the lift is caused by the air pressure below the wing, which is bigger than the pressure above the wing. This is the standard explanation for lift and Bernoulli's principle. Basically, what we see here is the essence of Bernoulli's principle and lift. Because of the difference in speeds, there is difference in pressure and lift is created. But why does the air move faster over the wing? A common misconception is that the air molecules have to meet in the end of the wing, and because the distance over the wing is longer, the air above the wing moves faster, so it has to meet the other flow that goes below the wing in the end. But this is actually a wrong explanation. The real reason that the air moves faster over the wing is that the external air pressure, which is actually the atmospheric pressure, is lower in that area. And in general, air will always move from a high pressure area to a low pressure area, and it will also move faster in that process. And that is in fact the reason that we have the speed difference between the two sides of the wing. The reason that air will move from a high pressure area to a low pressure area is related to the law of conservation of energy. Into describing other phenomena, such as the Bernoulli's principle, the Coanda effect, and the movement of air or fluid over curved surfaces. And this is something I will do in my next video. So I hope you enjoyed this video and more videos will follow.
Or ships flow through fluids, they set up behind them vortices, and when the flow is fast enough or the objects are big enough, they set up big turbulent wakes. The water is all churning around, and what's happening then is that the engine that's propelling the boat or the aeroplane or whatever, the energy of the fuel of that is actually being converted into this turbulence.
Will flow around a finite wing. The circulatory motion around the airfoils creates two big vortices at the wing tips.
Che si distacca dall'ala e che tende ad arrotolarsi a valle formando due nuclei vorticosi.
The intensity of these vortices is higher for low aspect ratio wing and for high lift coefficient. The vortex wake strongly interacts with the lift distribution along the wing because it influences the so-called downwash, which is the mass of the air that the wing pushes downward. For these reasons, also the induced drag is influenced by the vortex wake.
Which is shown here. This is a numerical simulation that's running on my iPad, solving the equations of motion for a fluid for flowing around a cylinder. This is a very common prototypical flow. We have a uniform upstream conditions on the left-hand side, and the fluid's moving from left to right. The cylinder is making it move around it, it speeds up, and then downstream we see a very unsteady wake. What we're plotting in here, we see these small little colored line segments. These are velocity vectors, the color indicating the velocity magnitude and the orientation of the segment showing the direction that the flow is going. As we talked about earlier, this is a Lagrangian velocity field. And then we're also showing on top of that some smoke lines that are being released upstream off the left-hand side. And every once in a while a thick blob of smoke comes in to sort of give us a time reference point. Now the question is, are these what we're looking at, do these represent the streamlines of the flow? And that's what we'll try and answer here at the end of the problem, and also talk about some of the ramifications. Streamlines are actually the most important of these three lines that we're talking about, but some of the other quantities are easier to generate. Alright, so a definition for what we see here is we could draw some streamlines in this figure. Let's go ahead and try and do that. I'll do that with this yellow ink here. Let me start at a point up here. It's relatively straight, and everywhere I go I'm going to try and interpolate and draw the curve so that it's tangent to what I think the velocity vector is at that point. And what we see is I go through here, I move, I'm going tangent to these velocity vectors, going around and through and down. Okay, so there's one. Let me move to another part a little bit lower. Let's start here. As I go in, I kind of I go around the cylinder, and then there's a little bit of a jog around in here. I come down, I get caught up in this eddy back here. Whoops. And this comes up through here, and I'm locally trying to stay tangent to these velocity vectors. Let's take one just to finish down here on the bottom. So we can see that those smoke lines that are in here, and with those blobs on it, were not at all streamlines, not in any general sense anyway. Here you can see I'm crossing over these smoke lines back here, and they're not coinciding. Up here, upstream of the cylinder, however, they do tend to follow these smoke lines. And as we go along here, I think those are kind of the same, and then they sort of deviate here. So somewhere around this point forward, at this instant, they seem reasonably close, but downstream all bets are off. So those smoke lines are definitely not streamlines. One last example for this, and then I'll sign off. Here's another flow.
trim the bottom edge off the bowl as best I can and trim the lip from round the outside, so that now fits fairly close. So I'll drill a hole in there so the motor can fit from the outside, sorry, from the inside. And then we've got to figure out how we're going to mount it on the car. I've mounted it on one of my good old faithful rubber band powered car chassis. So we'll see if it works. That seems to work. Oh, I can smell the motors overheating. Because that's really only a 1.5 volt motor and I'm running it on 9 volts. I'll let it cool down and then we'll give it another run. The main problem with it overheating is it melts the hot glue that I got it holding in place with. Well, that and the fact that it burns out. I'll give it one more go, but I think I may have cooked that motor. That'll do. There's a definite smell of hot wire or hot motor at the moment, and that's hot to touch if I put my finger actually on the motor.
Suck air in and blow it over the curved surface of the disc. This causes a drop of air pressure on top of the disc. The engine used here is a cheap one from a small vacuum cleaner. As you can see, it gives about 288 grams of thrust. The engine uses 652 watts, so that's only 0.44 grams per watt. That's not enough to lift its weight, but enough to push a little car, or maybe an aircraft. More on my site at www.laserworks. So one would expect the air to flow out of the fan horizontally in all directions, but due to the Coanda effect, the air bends down to almost 90 degrees. The airflow is being pushed down by the air above, because the pressure of the air in between the flow and the curved surface is reduced by the suction of the airflow. Next, another example of the Coanda effect, where I used smoke to make the flow visible.
보통 이 상태로 쓰거든요, 얘가. 이걸 크기 상대 크기를 이렇게 제가 좀 상대 크기 됐습니다. 이제 한번 기초하고 일단은 아까 해주신 것만 일단 기억만 해주세요. 이렇게 해놓고 이게 LED로 하면 공격도 반원만 그리게 해놨어야 되고 얼마나 얼마나 속도를 좀 빠르게 해놓으면